Hello everyone, this is Brian Orlasan Cordova and welcome back to another calculus class. So for our topic is tests for convergence and divergence of infinite series. Number 6, we have the limit comparison test. So theorem, suppose that a sub n is greater than 0 and b sub n is greater than 0 for all n greater than or equal to big N, where that is an integer. If the limit of the ratio of a sub n over b sub n as n approaches to infinity is equal to positive number c, then the summation of a sub n and the summation of b sub n both converges or both diverges. Number 2, if the limit of the ratio of a sub n over b sub n as n approaches to infinity is equal to 0, and the summation of b sub n converges, then the summation of a sub n converges also. Then number 3, if the limit of the ratio of a sub n over b sub n as n approaches to infinity is infinite and summation of b sub n diverges, then the summation of a sub n diverges also. So we have the conditions for the limit comparison test. So proof for number 1, using limit definition. So there exists a big N such that for all small n, there is an epsilon which is equal to c over 2 and L, the limit is equal to c. If n is greater than big N, it implies that the absolute value of a sub n over b sub n minus the limit c is less than the epsilon c over 2. Now solving for the inequality, we have negative c over 2 less than a sub n over b sub n minus c less than c over 2. Adding c on all sides, we have, so from negative c over 2, magiging positive na siya. A sub n over b sub n, mawawala na yung c. Then c sub c over 2 would be plus c, we have 3c over 2. Then multiplying b sub n on all sides, we have c over 2 times b sub n, a sub n na lang, and 3c over 2 times b sub n. Using a direct comparison test, if the summation of b sub n converges, so from the right side, so kung convergent ito, therefore yung smaller n terms sa kanya would be convergent also yung series na yon. And if b sub n diverges, if this one diverges, so a multiple of b sub n, then this one also diverges since this is not bounded anymore. So yung proof for 1 lang ang bibigay ko. So examples, test whether the following series are convergent or divergent. So example number 1, we have 3 over 4 plus 5 over 9 plus 7 over 16 plus 9 over 25 plus so on and so forth, which is equal to the summation of 2n plus 1 over n plus 1 quantity squared, where n starts from 1 to infinity. So this is equal to, expand natin yung denominator. So as solution, let a sub n is equal to the summand. For large n, we expect a sub n to behave like 2n over n squared. So hindi na natin papansinin yung smaller terms dun sa both numerator and denominator. And this is equivalent to 2 over n. So let's have a b sub n where it is equal to 1 over n. Since the summation of b sub n is equal to a summation of 1 over n, which is a divergent harmonic series, the limit of the ratio of a sub n over b sub n is equivalent to the limit of 2n squared plus n, since minultiply natin siya ng n sa denominator of the denominator over the denominator ng n squared plus 2n plus 1. And evaluating the limit, so by L'Hopital's rule, re-channel it until we reach the limit of 2, which is greater than 0. And by part 1 of the limit comparison test, since the limit of the ratio is greater than 0 and b sub n diverges, a sub n also diverges. Example number 2, we have 1 plus 1/3 plus 1 over 7 plus 1 over 15 plus so on and so forth. So this is equivalent to the summation of 1 over 2 raised to n minus 1. So as a solution, let a sub n is equal to the summand, so 1 over 2 raised to n minus 1. For large n, we expect a sub n to behave like 1 over 2 raised to n. So let our b sub n is equal to 1 over 2 raised to n. Since the summation of b sub n is equal to the summation of 1 over 2 raised to n, which is convergent since as n increases, the denominator increases and a sub n approaches to 0. So by the n-term test, it converges, and the limit of the ratio of a sub n over b sub n is equal to limit of 2 raised to n over 2 raised to n minus 1. And by rationalizing, we have the limit of 1 over 1 minus 1 over 2 raised to n. And since as n approaches to infinity, this will become 0. So 1 over 1 is equal to 1, which is greater than 0. So by part 1 of the limit comparison test, since the series of b sub n converges, then the series of a sub n also converges. So number 3, 1 plus 2 ln of 2 over 9 plus 1 plus 3 ln of 3 over 14 plus 1 plus 4 ln of 4 over 21 plus so on and so forth, which is equivalent to the summation of 1 plus n ln of n over n squared plus 5 from 2 to infinity. So solution, let a sub n is equal to 1 plus n ln of n over n squared plus 5. For large n, we expect a sub n to behave like n ln of n over n squared, since we disregard the smaller valued terms, so constant 1 and constant 5 in the denominator, which is, can cancel n on numerator and denominator, so this is equal to ln of n over n, and that is greater than 1 over n, which is the harmonic series, for n greater than or equal to 3, since you start with n is equal to 2 dun sa a sub n mo. So let's have b sub n is equal to 1 over n. Since summation of b sub n is equal to the harmonic series na nagda-diverge, so the limit comparison of the a sub n over b sub n is equal to a sub n times n, since yung b sub n is 1 over n, times n natin yung numerator, which is equal to infinity, since if we divide all terms by n squared, so the denominator would be 1. As n approaches to infinity, this will become 0, and this one will be 0 plus ln of n. Since n approaches to infinity, ln of n approaches to infinity also. So this is by part 3 of the limit comparison test. Since the limit of the limit comparison is infinite and the summation of b sub n diverges, then the summation of a sub n diverges also, which is our given series. So number 7, the absolute convergence. A series summation of a sub n converges absolutely if the corresponding series of absolute values, this summation of absolute values of a sub n, converges. So the theorem, this is the absolute convergence test. If the summation of absolute values of a sub n converges, then the series a sub n converges. So as a proof, for each n, so the negative absolute value of a sub n is less than or equal to a sub n is less than the positive absolute value of a sub n. Adding absolute value of a sub n on all sides, so this will become 0, a sub n plus the absolute value of a sub n, then absolute value of a sub n plus absolute value of a sub n is twice of it. And if the summation of absolute value of a sub n converges, then the upper bound summation of two absolute values of a sub n converges. And by the direct comparison test, yung series sa gitna, the summation of a sub n plus absolute value of a sub n also converges, since it would be bounded by the series on the right side. Since a sub n is equal to a sub n plus absolute value of a sub n minus the absolute value of a sub n, so the summation of a sub n is equivalent to the summation of that expression. So we can separate the summation of the terms. So the summation of a sub n plus absolute value of a sub n minus the summation of absolute value of a sub n. That is actually the difference of two convergent series. Since the series of absolute value of a is convergent, and this sum of a sub n and absolute value of a sub n is also convergent, so this one is also convergent. Therefore, the series of a sub n without the absolute value is also convergent. Examples. So the summation of the alternating series -1 raised to n plus 1 times 1 over n squared from 1 to infinity is equal to 1 minus 1/4 plus 1 over 9 plus minus 1 over 16 plus so on and so forth. So the given series have the corresponding absolute values is convergent series. So that is the summation of 1 over n squared. Absolute values niya is nawala lang yung mga negative signs. So this is a positive series. So it is a P series with P is equal to 2, which is greater than 1. And by P series test, that is a convergent series. Example number 2, the summation of sine n over n squared is equal to sine 1 over 1 plus sine 2 over 4 plus sine 3 over 9 and so on and so forth, which contains both positive and negative terms because of the trigonometric function sine. And if we reach sine 180, after that, the terms would be negative. After sine 360, it will become positive again. Now, we should test the absolute value. So the series of the absolute value of sine n over n squared, which is convergent with comparison with the P series, with P is equal to 2, since the absolute value of sine n is less than or equal to 1 for all values of n, since sine of any number only reaches from -1 to +1 and back and forth. Convergence and divergence test number 8, the ratio test. So it measures the rate of growth or decline of a series by examining the ratio a sub n plus 1 over a sub n. For geometric series, the summation of a times r raised to n, the rate is constant. That is r. And it converges if and only if the absolute value of r is less than 1. So theorem for the ratio test, let the summation of a sub n be series and suppose that the limit of the absolute value of the ratio of a sub n plus 1 over a sub n as n approaches to infinity is equal to rho, then the series converges absolutely if rho, or the limit, is less than 1, and the series diverges if rho is greater than 1 or rho is infinite. And the test is inconclusive if rho is equal to 1 or the limit is equal to 1. So examples. The summation of 2 raised to n plus 5 over 3 raised to n, where n is from 1 to infinity. So by ratio test, we have 2 raised to n plus 1 plus 5 over 3 raised to n plus 1 over yung a sub n is 2 raised to n plus 5 over 3 raised to n, which is equal to 1/3 because the denominator 3 raised to n plus 1 over 3 raised to n is equal to 1/3, and yung numerators na 2 raised to n plus 1 plus 5 over 2 raised to n plus 5. Now let's multiply all terms by 1 over 2 raised to n, both numerator and denominator. So this will become 1 over 3 times 2 plus 5 over 2 raised to n over 1 plus 5 over 2 raised to n. Taking the limit, this approaches to 2/3 only, which is less than 1. So the series converges absolutely because rho, or the limit, is less than 1. Number 2, the summation of 2n quantity factorial over n factorial times n factorial. Then a sub n plus 1 is actually equal to 2n plus 2 because we substitute n by n plus 1, so we distribute 2. So the numerator would be 2n plus 2 quantity factorial over n plus 1 quantity factorial plus n plus 1 quantity factorial. So the ratio or the absolute ratio would be the denominator of a sub n would be multiplied to the numerator. Dun. Then yung numerator would be multiplied to the denominator of this one. So n factorial times n factorial times 2n plus 2 quantity factorial over 2n factorial times n plus 1 factorial times n plus 1 factorial. Now we can expand to get a common factor so that we can cancel things out. So we have 2n plus 2. So ang kasunod niyang factor is 2n plus 1. Then minus 1. We have 2n quantity factorial. So we can cancel 2n factorial with the denominator to n factorial. And n plus 1 factorial, the next would be n factorial. So meron tayong dalawang n factorial dito, saka dito. So what would remain is 2 times n plus 1 times 2n plus 1 over n plus 1 times n plus 1. So we cancel out n plus 1. So we have 2 times 2 is 4n plus 1, which is 2 times 1 is 2. So the denominator is n plus 1. So evaluating the limit, this approaches to positive 4. So since it is greater than 1, the series diverges because the limit is greater than 1. Number 9, the root test. It is used when the formula of a sub n is too complicated for the other tests. So the theorem states that let the series of a sub n be any series and suppose that the limit of the nth root of the absolute value of a sub n as n approaches to infinity is equal to the rho. Then letter A, the series converges absolutely if rho is less than 1, just like the ratio test. And B, the series diverges is if rho is greater than 1 or it is infinite. And the test is inconclusive is rho is equal to 1. So the conditions are the same with the ratio test. So example, consider the series with terms a sub n is equal to, so it is a piecewise defined function. So a sub n is equal to n over 2 raised to n if n is odd, and 1 over 2 raised to n if n is even. So that is the summation of a sub n is equal 1 over 2 raised to 1, since n is odd, plus 1 over 2 raised to 2, plus 3 over 2 raised to 3, since it is odd, and so on. So as a solution, applying the root test, the nth root of the absolute value of a sub n is the nth root of n over 2 if n is odd, and 1/2 if n is even, because since may nth power sa denominator, mawala yan kapag tinik natin yung nth root. We have 1/2 less than or equal to the nth root of the given series, and it is equal or less than dun sa nth root of n over 2. So it is bounded by these two values. So 1/2 up to nth root of n over 2. Since nth root of n approaches 1, so it is one of the common occurring limits. So the right-hand side would be approaching to 1/2 also. So by sandwich theorem, both boundaries is 1/2. So the limit of the nth root of the absolute value of n is also equal to 1/2. And it is less than 1. Therefore, the series converges absolutely by the root test. Example number 2, the summation of n squared over 2 raised to n. So nth root of absolute value of a sub n is equivalent to nth root of n squared over 2 raised to n. And we can distribute the roots on both numerator and denominator. And the denominator would be 2 only. And by manipulating the roots and the power on the numerator, we can have the nth root of n quantity raised to 2, which approaches to 1 squared over 2, and it is equal to 1/2. And that is less than 1, therefore the series converges absolutely. Number 3, summation of 2 raised to n over n cubed. So nth root of absolute value of a sub n, so nth root of 2 raised to n over n cubed is equal to, so Same process with the example number 2. So, yan. Which approaches to 2 over 1 cube, which is equivalent to 2. And it is greater than 1, therefore the series diverges. And number 4, the summation of 1 over 1 plus n raised to n. The nth root of the absolute value of a sub n is equivalent to nth root of 1 over 1 plus n raised to n. It's equivalent to 1 over 1 plus n since na-cancel out yung root and yung power. And it approaches to 1 over infinity because as n approaches to infinity, it is equal to 0. Since this is less than 1, therefore the series converges absolutely. Last test, we have the alternating series test. So the alternating series is a series in which the terms are alternately positive and negative. So a sub n is equal to, so the alternating factor would be a negative. So negative 1 raised to n plus 1 times u sub n, or a sub n is equal to negative 1 raised to n times u sub n. So u sub n is equal to absolute value of a sub n. Our theorem, the series, the summation of negative 1 raised to n plus 1 times u sub n is equivalent to this one, u sub 1 minus u sub 2 plus u sub 3 minus u sub 4 plus so on and so forth. Converges if all three conditions are satisfied. So the u sub n's are all positive. So by taking the absolute value of a sub n, the u sub n's are all positive. The positive u sub n's are eventually non-increasing. Means that u sub n is greater than or equal to the next term for all n greater than or equal to the big N. And eventually, u sub n's approaches 0. So since it is not increasing and it decreases and approaches to 0. So as a proof, assume that big N is equal to 1. So if n is even, n is equal to 2m, as long as there is a factor of 2 times any integer. Then the sum of the first n terms is, so rather than s sub n, we have s sub 2m is equal to u sub 1 minus u sub 2 plus u sub 3 minus u sub 4. So we group the terms by summation of differences. So this shows that s sub 2m is the sum of m non-negative terms. So they are positive since u sub 1 is greater than u sub 2 and u sub 3 is greater than or equal to u sub 4 and so on. So the sum of m non-negative terms. And if by combining other terms, we have u sub 1 minus u sub 2 minus u sub 3 because we factor out the negative values of the other terms. So we can have a u sub 1 minus subtracting of differences. This shows that the sum s sub 2m is less than or equal to u sub 1. So u sub 1 is the most largest value of terms. Thus, the succeeding u sub n's is less than or equal to u sub 1. So, much smaller na yung mga next terms. So, if n is odd naman, n is equal to 2m plus 1. So, we have the sum s sub 2m plus 1 is equal to s sub 2m plus u sub 2m plus 1. So, we have just added a term so that n is odd. So since both the sequences of s sub 2m and s sub 2m plus 1 are non-decreasing and bounded above, and the limit of s sub n is equal to L, this implies that if n is even, we have the limit of s sub 2m is equal to L, and if n is odd, we have this one. This implies that L is equal to L plus limit of u sub 2m plus 1 as m approaches to infinity. Therefore, the limit of the last term is equal to 0. And in general, all terms of u sub n's approaches 0. So let's have an illustration where we have this one. So from 0, we have u sub 1. Then we subtract u sub 2. Then we add u sub 3 and minus u sub 4. Then the partial sums would actually be converging to L. Then the three conditions are satisfied with n is is equal to 1. Examples, the alternating harmonic series. So negative 1 raised to n plus 1 times 1 over n is equal to 1 minus 1 half plus 1/3 minus 1/4 and so on. Clearly satisfies the three requirements of the alternating series test with n is equal to 1. Therefore, it converges. The alternating p series, which is summation of negative 1 raised to n minus 1 over n raised to 3 halves, which is equal to 1 minus 1 over 2 raised to 3 halves plus 1 over 3 raised to 3 halves minus 1 over 4 raised to 3 halves plus so on and so forth. U sub n is equivalent to 1 over n raised to 3 halves. So it is positive. So that is the absolute value of a sub n. And u sub n plus 1 is actually less than or equal to u sub n. So the next term would be smaller. Then the limit of the u sub n as n approaches to infinity is equal to 0. So the p series with p is equal to 3 halves is greater than 1, therefore the series converges. So in summary, for the n-term test, so if the n-term a sub n approaches to 0, the series converges, and otherwise it diverges. Number 2, in geometric series, the summation of a times r raised to n converges if the absolute value of the common ratio r is less than 1, otherwise it diverges. In p series, the summation of 1 over n raised to p converges if p is greater than 1 and otherwise it diverges. So number 4, the series with non-negative terms. We can use the integral test if the integral of f of x dx from 1 to infinity where a sub n is equal to f of n exists, it converges, otherwise it diverges. So we can also use the comparison test and limit comparison tests to compare the given series to a known series. And for series with some negative terms, we have the ratio test, where the limit of the absolute value of the ratio a sub n plus 1 over a sub n is equal to rho. And the root test, the nth root of the absolute value of a sub n is equal to rho, converges if rho is less than 1. And lastly, we have the alternating series test. The summation of a sub n converges if it satisfies the three conditions. So the next topic, we have the power series, Taylor and Maclaurin series.